We're getting into chapter 10 today on Introduction to Rotational Motion and Angular Momentum. And it starts off with this spinning figure skater who increases her rate of spin by pulling her arms in. Let's check out the little video, shall we? It gets into figure skating and talking about physics. Again, sports. But they do talk about angular momentum, L, and how when it's conserved, the idea is that if you can reduce your moment of inertia, you can increase your angular velocity. So that's a kind of cool thing. So this is all about things that are rotating, and it starts off by talking about angular velocity. And if you remember, way back in chapter 6, we talked about rotation angle delta theta and angular velocity delta theta divided by delta t. Okay, so the idea there is that when the angle of something changes as it's turning, there's an angular velocity, okay, the rate of change of the theta. So up in section 10.1, the idea here is that now that we have this, instantaneous angular velocity, there can be a rate of change of angular velocity. And so they define this quantity alpha. Angular acceleration is the rate of change of the angular velocity. So this is very analogous to when we had position. The rate of change of position was velocity. The rate of change of velocity is acceleration. So now we have angular position. The rate of change of angular position is angular velocity. The rate of change of angular velocity is angular acceleration. And you're just basically using the Greek letters instead of the English letters. So now actually this definition, when you don't use calculus, you're just doing the change delta omega divided by delta t. This is the average acceleration. But I think in this book, they really just seem to always assume that angular acceleration is constant, which I guess it sometimes is, but really it should be stated. Here's a teenager puts her bicycle on its back and starts the rear wheel spinning from rest to a final angular velocity of 250 RPM in 5 seconds. This should really say either calculate the average angular acceleration in radians per second squared, or you could say assume the angular acceleration is constant and then compute it. But it's I think you just have to assume that it's constant. In this entire chapter, really. It talks a little bit about how you relate the tangential acceleration to the angular acceleration. There is an equation for these things. The real useful equation is actually, it's 10.13 right here. The tangential acceleration, which is, causing something to speed up in meters per second squared, is equal to r times alpha, where alpha is in radians per second squared. So this is a super useful equation if you're trying to find the tangential acceleration given alpha, or if you have alpha, or you have the tangential acceleration and you're trying to find alpha, you can divide by r. So there are some examples of that. So for example, when you have rolling without slipping, the angular acceleration of the tires is alpha, and the tangential acceleration is the acceleration of the object that's rolling without slipping, sometimes called linear acceleration. So here's a great table which relates the rotational variable, the translational variable, and their relationship. And in each case, it's just r. So theta is x over r, omega is v over r, with v is this tangential velocity, and alpha is a tangential over r. Section 10.2 is kinematics of rotational motion, and they do mention very quickly here, as in linear kinematics, we assume a, in this case the tangential acceleration, is constant, which means that the angular acceleration alpha is also constant because a equals r times alpha. So that's really the only time they state it, but it's super, super important. And in this entire section, they assume alpha is constant, which it could be. So when that's the case, you can actually, with these r's, figure out pretty easily that omega equals omega 0 plus alpha times t. This is the analogous kinematics equation for v equals v0 plus at, which is you learned long ago in chapter 2. Now, just with angular variables, you get an equation which looks very similar. And it's good to make connections between chapter 2, one-dimensional kinematics, and here in chapter 10, the rotational kinematics. And here they have a table actually that shows the old equations, so the old equations here, translational, that you should recognize from chapter 2, and now just basically going to Greek letters, same equations, but now you're talking about something rotating instead of something moving in a straight line. And here's a nice little reminder that we're assuming constant acceleration in all these cases. And there's good examples here. For example, deep sea fisherman hooks a big fish that swims away from the boat, pulling the fishing line from his reel. The whole system is initially at rest, and the fishing line unwinds from the reel at a radius of 4.5 centimeters from its axis of rotation. The reel is given an angular acceleration of 110 radians per second squared for 2 seconds. So what they do there is they say that it starts from rest, omega 0 is 0, and then alpha is 110 radians per second squared, and t is 2 seconds. So you can find the final angular velocity. And then, since it's a reel, it's a little bit like rolling without the slipping. The string unwinds from the reel at the same linear rate as the tangential velocity. So you multiply by r, and you can get the speed of, I guess, the fish on the end of the reel. And in C, they ask you for the number of times the reel rotates. And so that you can find theta, which is the angular displacement of that wheel. Every time it goes around 360 degrees, theta changes by 360 degrees, right? So you can find theta by using that analogous kinematics equation. Remember, x equals, I think it was v0 plus 1/2 at squared. Here you've got theta is equal to omega 0t plus 1/2 alpha t squared. And you can plug in all those things. It starts from rest, so you just got alpha times t squared, 220 radians. And every 2 pi radians, you divide by 2 pi to get how many revolutions. And there are several other examples in this chapter, which I would like you to go through. Section 10.3, dynamics of rotational motion and rotational inertia. The idea here is that we're no longer looking at static equilibrium where there's torques that balance each other. Now we have actual rotation. So if we have a wheel, for example, that has some angular acceleration, it's because you're applying a force. So you apply a force, and the greater the force, the greater the angular acceleration, which sort of makes sense. But also, if you push on a spoke closer to the axle, the angular acceleration will be smaller. So there's a couple things going on here. And they go through a derivation and come up with, for a particular mass, torque equals mr squared times alpha, where m is like a point mass that's going around on a circular path. So this is what's called the rotational analog of Newton's second law. F equals ma. Instead of F, you've got torque. And instead of A, you've got alpha, so the angular acceleration. And this mr squared for a particular particle is what is called the rotational inertia, or sometimes called moment of inertia, of a point mass m, a distance r from the center of rotation. This is an example of a point mass m that's going around in a circular path. You press it with an F, a force F, giving it a torque. This will give it some angular acceleration on that path. Now, that's for a point mass going in a circular path. If you have a rigid body that is rotating, like some actual shape, then you have to sum up the mr squareds for every particle in that object. And when you do that, you call it I. I is analogous to m. And so it's not always mr squared, it's the result of some sort of integral. But now we start writing I. And here again is another way of writing Newton's second law for rotation. The angular acceleration is the net torque divided by I, the rotational inertia. So they give you a problem-solving strategy. Once you've got a object that could be rotating, draw an extended free body diagram. So draw and label all the external forces acting on the system, including where they're acting. The net torque equals I times alpha. Of course, you need a pivot point as well. So it turns out you do need calculus and an integral to calculate what the rotational inertia is for different particular shapes. Now, if you have a hoop that's rotating about an axis that's going through its center, every particle of little mass m is at the same distance r. So when you add it all up, you just get m, the total mass of the hoop, times r, the radius of the hoop squared. Sort of makes sense. But if you, for example, have a solid disk where it's all filled in the middle, you end up with mr squared over 2. Some of the particles are right at 0 r, and some of them are halfway. It ends up being mr over 2. And so there are different shapes here rotated about different axes, and you usually get the mass times something to do with its size, could be L, could be R, squared, and then there's usually a fraction, over 12, over 3, over 5, depending on the shape. You could even have a hoop, it depends on the axis, right? So hoop going with the axis going through the center, it was mr squared. If you spin it then around a vertical axis through it, you end up with a different rotational inertia, mr squared over 2. I guess it sort of makes sense, right? Because now more of the mass is located closer to the axis. The idea with all of these things is that the farther the mass is away from the axis, the larger the rotational inertia. And you can use Newton's second law to find the rotational angular acceleration of various objects. Here they have a solid disk for which you use mr squared, 1/2 mr squared, and then they have a person at some particular distance. You consider that like a particle, mr squared, at some distance. Section 10.4 is on rotational kinetic energy. So when anything is rotating, it has some kind of kinetic energy. You can imagine all the particles are certainly moving. So how much kinetic energy does it have? Well, one way to figure this out is to calculate the work. Remember, in linear motion, the net work on an object was the change in its kinetic energy, and that was force times the displacement. Here with rotation, the net work can be the net torque times the angular displacement. And remember, from Newton's second law for rotation, the net torque is equal to the rotational inertia times alpha. So it's I times alpha times theta should be the energy that it picks up. And if you use the rotational kinematics equations, you can rearrange this and you get that the net work is 1/2 I omega squared. And that looks really similar to 1/2 mv squared for translational kinetic energy. So this is called rotational kinetic energy. If an object has a moment of inertia I and an angular velocity omega, it's storing rotational kinetic energy 1/2 I omega squared. It talks a bit about flywheels here. A flywheel is a massive disk that is spinning inside something, and if you slow it down, you can extract energy from it. So it's almost like a big battery. It's a way of storing energy. There's some examples of this. Helicopters, and then the can of soup race. So an idea here is that as something is rolling down a hill, it's speeding up, so it's gaining kinetic energy, 1/2 mv squared, but it's also rolling without slipping, so it's rotating. So it has 1/2 I omega squared as well. So in fact, as something rolls without slipping down a hill, its initial energy is in gravitational potential energy, but its final kinetic is split into two parts, the translational kinetic energy plus the rotational kinetic energy. And section 10.5 is on angular momentum. So we had in previous chapters work and energy, then momentum, all in linear motion. Now we have in these sections rotational energy and rotational momentum. Very analogous. So angular momentum, which is called L, is I times omega. And this does turn out to be a vector quantity. Unlike rotational kinetic energy is a scalar, angular momentum is a vector because we say that the rotation, the angular velocity, omega, is a vector. So we're using those same moment of inertia equations and just multiplying times omega to get angular momentum. And the idea is that the net torque on a system is the rate of change of this angular momentum. So you can have almost an angular impulse. The net torque times delta t is this angular impulse, and that gives you the change in angular momentum. Very, very similar to how the F net delta t was the impulse in a linear sense, and it gave you a change in p, the momentum. But this is just a rotational version of it. There's a few more examples. And then we get to conservation of angular momentum. If there is no net torque on a system, then the angular momentum doesn't change. So if net torque equals 0, then the rate of change of angular momentum is 0, so L is some constant. So we can say L is L prime. Before some process or collision or something, and after some process or collision, angular momentum is the same. And this is where we get to that skater who's spinning with initially her arms outstretched, and she's got some omega, is angular velocity, but she has a high rotational inertia or moment of inertia because her arms are outstretched, and so more mass is farther from the rotation axis, which is in the middle. If she then brings her arms in, what she does is I prime here is the new moment of inertia, which is less. More mass now is concentrated towards the axis, so I has decreased, but there's no net external torque, or not much, so what happens is that L, the angular momentum, is conserved. So in order to compensate for I prime being less, omega prime has to be bigger. What's omega? Omega is that spin rate, is the angular velocity. So she ends up spinning a lot faster with her arms in stretch due to conservation of angular momentum. And that's actually exactly how the solar system formed 4.6 billion years ago, is that there may have been a little bit of initial rotation or angular velocity just due to random thermal motions of the gases in the solar nebula, the hydrogen that originally formed the solar system. But then as gravity brought it all together and decreased that moment of inertia, the angular momentum was conserved, and so the angular velocity increased. And then of course, once something is spinning, it does tend to flatten out and form a disk. And so that's why all the planets in the solar system are orbiting the sun in one sort of plane, orbital plane. Section 10.6 is on collisions of extended bodies in 2 dimensions. When things strike each other, they not only transfer momentum, they transfer angular momentum because they rotate. And an example of conservation of angular momentum is given here. I'll zoom in a little bit. A disk slides towards a motionless stick on a frictionless surface, and at B, the disk hits the stick at one end and adheres to it, and they rotate together. So this is a perfectly inelastic collision where this moving object then sticks to the initially stationary object. So what they do is they conserve, in this case, angular momentum around the pivot point, which is, there's a nail, I guess, in the bottom of the stick here. Angular momentum is conserved around the pivot. So to find the angular momentum before, you just take the velocity or the speed v of that mass, which is perpendicular to this vector r. Omega is v over r. Moment of inertia of a mass at that distance r is mr squared. So you take mr squared, which is I, times v over r, and you end up with m times v times r, is the angular momentum of the mass, which is actually moving in a straight line as it goes past this point where you define r equals 0. And then after, well, it really is now rotating at some final angular velocity omega prime. Now the moment of inertia is different because it includes the stick and the mass. So you have to add the moment of inertia of the mass plus mr squared over 3, which is the moment of inertia of the stick rotated around its end. And you can find omega prime, the final angular velocity of the stick with the mass stuck in the end of it. They also ask you for the kinetic energy. You can find the kinetic energy before, and the kinetic energy after is 1/2 I prime omega prime squared. It's the rotational kinetic energy. And it turns out to be quite a lot less, which is just what you would expect. What's interesting, though, is when you compute the linear momentum, the disc that hits it and the center of mass of the stick after it's rotating, you get 2.2 kilogram meters per second, which is bigger than the initial momentum. And they describe that as apparently the stick pushes backwards on the nail when it's first struck by the disc, and the nail's reaction, consistent with Newton's third law, is to push forward on the stick, imparting momentum to it in the same direction in which the disc was initially moving. So it actually increases the momentum of the system. So that's because the nail is connected to the earth, and the earth can then transfer momentum. So whenever something is connected to the earth, either by the floor or by a wall or something, momentum actually is not conserved because it gets transferred by the earth. And the last section of chapter 10 is about gyroscopic effects, the vector aspects of angular momentum. So angular momentum L has a direction which is perpendicular to the plane of rotation. So if something's rotating in a plane, you say that the angular momentum vector, you define it to be a vector which is perpendicular to that plane of rotation. So nothing's actually moving in that direction, but we define the L vector. And there's two perpendicular directions to a plane. You pick it by using the right-hand rule. So you take your right hand, you curve your fingers in the direction of the actual rotation, the way they naturally curl, and now your thumb points in that perpendicular direction for the L vector. So here is something that's rotating counterclockwise. Then you use your right hand to see that if it's counterclockwise as viewed from above, the L vector is up. And it turns out that the net torque is the rate of change of this L vector. So torque also has a vector sense to it. And the way that goes is that torque is a cross product. And so of R cross F. So R is a vector which goes from the pivot point out to where the force is applied, and F is that force that's applied. And whenever you do the cross product of two vectors, you take the first vector and have your fingers sort of outstretched. That's the direction of the first vector, R. And then the second vector, F in this case, you bend your fingers towards that second vector, and then your thumb points in the direction of that cross product. So the cross product is always perpendicular to the plane of the two vectors that are being crossed. And so R cross F is tau. And tau is also the direction of any little change in L, the angular momentum. So what's interesting is that if you have a wheel that's spinning in a vertical plane here, that would give it, see if it's rotating here counterclockwise, that would mean that its L vector is off to the right here, this big L vector. If then there's a torque, you try to twist it or something, like by pushing a force down and a force up, what that will do is create a torque R cross F, and so it's into the page there, so it'll rotate this L vector into the page, which is not what you would expect. You're trying to tilt it, I guess, this way, clockwise, but what ends up is you end up tilting it around a different axis. And that is how a gyroscope works. As something is really spinning, if gravity tries to tilt it in one direction, like down, what happens is that instead it goes in a horizontal path. And that is it for chapter 10. My name is Jason Harlow, and I hope you enjoyed this video. If you have time, please fill out the feedback form on my Google Forms available in the description to this video. There's also a link to the Google Classroom where there's a public discussion forum and a place where you can ask me a lot of questions. Also available as a link in the description to this video. I look forward to hearing from you. Take care.